Hey, Cheryl. So I keep hearing about quantum computing being this game changer, right? But, how does it actually fit into something as massive as climate modeling? I mean, our current models, they seem pretty advanced.
Oh, Heidi, it's a huge deal, a really huge deal. And honestly, our current Earth system models, or ESMs, they're incredible, don't get me wrong, but they're kind of hitting a wall. Think about it. Billions of interacting variables, right? The whole climate system is it's chaotic, intricate, and computationally, it's humanity's most demanding problem. The models we have, they do their best, but they rely on these significant workarounds. Workarounds? Like what exactly? I always thought they were just like super accurate simulations. Well, not exactly. The thing is, to make them even run, we have to divide the globe into these really large grid cells, right? And because those cells are big, a lot of critical small-scale stuff, like how clouds form or ocean eddies, they can't be simulated directly. So scientists use parameterizations, basically simplified equations, and that introduces a lot of uncertainty. Plus, there's the whole butterfly effect thing. Tiny inaccuracies get amplified, and suddenly your long-term prediction is totally different.
Wow. So it's like a huge estimation then, not a precise forecast.
Exactly. And for really deep problems, like simulating molecules in the atmosphere or new materials for carbon capture, classical supercomputers just can't handle the exponential complexity. It becomes intractable.
Okay, so our current models have these big blind spots, essentially. So where does quantum computing step in? What even is a qubit beyond just a superbit?
Oh, this is the exciting part, Heidi. It's not just a superbit, it's fundamentally different. Classical computers use bits, either 0 or 1, but qubits, they leverage quantum weirdness. They can be 0, 1, or both simultaneously. It's called superposition. And this is key because with just n qubits, a quantum computer can represent 2 to the power of n states at once. So imagine for climate models, instead of exploring scenarios one by one, you're exploring countless environmental scenarios and variable combinations in parallel. It's a game changer for speed and comprehensiveness.
Whoa, so it's like seeing all possible futures at once, sort of? That's wild.
Kinda, yeah. And then there's entanglement. Qubits can get linked, right? The state of one instantly influences another, even if they're far apart. This correlation allows for highly complex interwoven calculations. It's almost like the quantum computer can naturally understand the chaotic and interconnected nature of Earth's climate in a way classical systems just can't, quite grasp. These two phenomena, they unlock exponential processing power for really tough problems.
That's mind-blowing. So if it can understand the chaos better, what does that actually mean for specific improvements in climate modeling? What problems can it actually solve that we couldn't before?
Okay, so many things, honestly. First, it can dramatically speed up solving those fundamental differential equations that are the core of climate models, especially fluid dynamics. Quantum linear algebra solvers, they offer exponential improvements for certain linear problems. Then there's parameterizations. Remember those simplified equations for clouds and turbulence? Quantum machine learning, or QML, can totally enhance those. We're talking about more accurate representations of small-scale processes. Research shows QML-based cloud cover parameterizations are possible, which is it's huge.
Wow, so fewer assumptions, more reality. That makes sense. What else?
Yeah, exactly. And model tuning, climate models have tons of adjustable parameters. Tuning them for accuracy is a massive computational headache. Quantum optimization algorithms like QAOA can search these huge parameter spaces way more efficiently, saving tons of time and resources. And then molecular simulations for things like atmospheric chemistry or new carbon capture materials, quantum computers are perfect for that. VQE can find ground state energies of complex molecules super accurately, potentially boosting carbon capture material efficiency by like 40%. It's pretty